All right, today we're going to get to section 1.3, which actually incorporates some of the algebra that you know and love. And you might find that you actually are a little bit more inclined toward this approach than the numerical or the graphical approach because of your exposure to algebra and how much you've worked with it. So a few things to get started. There are some basic limits that we're going to encounter. So these are our first three. If we have b and c as real numbers and n is a positive integer, then if you have the limit of a constant, right, b is a constant, so the limit of the b value, then it equals b. And I'm going to try and justify these at least a little bit as we go through to see that they seem reasonable. So let me state all of them because you guys are going to write them all in whether I keep talking or not. And then we'll go back and kind of think through the justifications for them. The second one says that if we have the limit of simply x as x approaches c, then its limit is c. And if we have the limit of x to the n as x approaches c, it's c to the n. Now, the first two are the easiest ones to justify either with a graph or with a numerical, like with a table. I'm going to choose to use a graph because I think that visually it's very nice. On the first one, if you have the equation y equals, and I'm going to use a number 5 just so that I have a number. It doesn't have to be 5, but y equals 5. What does that look like? Okay, so it's a line, it's a horizontal line specifically, right? It's a horizontal line at 5. And so all the way along that line, no matter where you are, that's not very straight, but pretend for a moment that it is, and this is my line at y equal 5, the y value is the same. It has absolutely no bearing on what x value you're at. You're always at y equal 5. So no matter where you plot the point that you're considering, it's a little too light. How about this one? Here or here or here, the limit from both directions is always 5, right? Because this is just a horizontal line. The second one also very nicely with a graph. We can talk about what happens. What does the line y equal x look like? Yeah, it's a straight diagonal, like a 45-degree angle right through the origin, right? Yeah, and so here's my graph for that. Again, roughly speaking, that's not great. Let's try it a little bit better. That's a little bit more convincing. So on this particular one, no matter what x value you're at, it's the exact same y value, right? Because that's what the equation says. So if x is approaching 5, y is approaching 5. If x is approaching 7, y is approaching 7. If x is approaching negative 432, then y is approaching negative 432. So they simply match. So you see the function itself, which is what's in here. This is my function, which is my y values. And my x values match because the function is y equal x. And then the third one is an extension of that same idea, right? If y is equal x to the n, and if we can evaluate the x with the x value, I can do the same thing when it has a power. So my x to the n becomes c to the n, whatever the c value is. All right, the next ones talk about what happens when the functions become more elaborate, right? These are very simple functions. We have a constant, we have a linear, and we have the polynomial that's just x to the n. So what happens when there's more involved? So again, b and c are real numbers, n is a positive integer, f and g are functions, and they have limits. Okay, so we're not talking about anything that has jumps in it or anything at the particular values. Okay, so these are nice, good functions. They're very what we call well-behaved. Okay, so when that happens, if the limit of f of x is L, and the limit of g of x is k, then we can say the following. If there's a scalar multiple b in front of f of x, then in a very sort of real way, this b value can come in front, and we're left with the limit of f of x, which is L. So we just multiply the b times the L. That's what's happening. So it just gets multiplied by whatever that limit would have been without it there. If we have these two functions added or subtracted, well, then we can add or subtract their limit values as well. And if we have the two functions multiplied, then we can multiply their limit values. Give it a sec, it'll come back. I have a couple more, and I know you guys are still writing in some of these details, but what I'd like to say in general is limits are very nice. The things that you expect to be true, they are. That's not going to happen when we get to derivatives and later on antiderivatives all the time. But for limits, it's true, right? If the functions are added, the limits are added. If the functions are multiplied, the limits are multiplied. Here in a minute on the next slide, when they're divided, they're divided. Everything that you kind of would hope that would be true is true when it comes to limits. So let's look at the last two. Same like direction set, I just don't have enough space on that other slide. So again, if the functions are divided, their limits are divided, provided that the limit k, like that value k, is not 0. If the value k is 0, we've got other issues to deal with, and we'll talk about those when they come up. But as long as we're not dividing by 0, this works. And the last one tells you what happens when there's an exponent to the whole function f of x. So it's sort of a glorified case of what happens when there was just an exponent on x itself, but you see the same thing happen. The limit is put in there, and then it's raised to that power. So all of those things are all well and good. And what they really allow you to do is what you probably suspected when you were in the middle of 1.2. Can't I just plug the number in for x? Some of you did it, I know, right? You're like, I'm pretty sure I can just do this. And sure enough, it seems to be working out all the time. So I think it's right. And maybe you didn't even think, you just assumed and moved forward. Well, you were right. You were right. As long as it actually gives you a value that, for example, doesn't have a 0 in the denominator kind of stuff, you can do that. So when we have these functions like this, I'm going to show you what's happening in a very literal way on number 1. This is the only one I'm going to show it for you too. So a lot of times in mathematics, all the properties are sort of working behind the scenes, allowing you to do what you already sort of intuitively expect you can. So let me show you what really is happening with the properties on the first one, to give you some sort of sense of how convenient and nice it is that you don't have to go back to the properties every time. So what this actually says I should be able to do from the properties on the previous two screens is I should be able to put the negative out in front, and I should be able to take this limit, what am I going towards, x equal 1, of the function x squared. And then I have a separate limit over here for the function 1 as x goes to 1. Okay, so I'm sort of separating the two limits into separate pieces from the addition. And I have the ability to move the negative out in front because that's a constant multiplier. Okay, those are two of my properties. And then my other two properties that are at play say that, okay, well, if I have x squared, that was one of that first set of properties that I told you about, we can simply evaluate that right there with the number 1 in for x. And if I have the limit of a constant, so the limit of the number 1, it is just 1. Right? That's all those properties that are at work. But because we're going to have those properties working for us in a very convenient way all the time, we can simply jump to the last step. We just evaluate our function at the x value it gives us for our limit. So what is negative 1 squared? It would be if the negative were being squared, but the negative's not being squared. Yeah, so it's negative 1. So be careful. That is really a tricky thing to be aware of. Only the 1's being squared. So I have negative 1, and then I have plus 1, so my limit is actually 0. Okay, so you might be asking, well, I mean, how much of that do I actually have to show you? Well, at least show me this. Show me that's what you're doing, that you're actually plugging the number in. You don't have to show me any simplification or anything like that. Just show me that you're plugging the number in if that's what you're doing in the problem, okay? Now, if I were to do the next one and I were to write out all the limits, it would be really messy because I have a division property and I have the addition and I have the subtraction property. So there's 3 separate limits. And then I would pull out the coefficients of each of the pieces as well, right? There's a lot of properties going on behind the scenes that we get to kind of take for granted a little bit, and we get to utilize them because we have them, and we get to simply evaluate our function at -3, at least as long as it doesn't make the denominator 0, and it doesn't, so we're in good shape on this one. So I have 2 times -3 minus 3 on top, and -3 plus 5 on bottom. 2 times -3 is -6 minus 3 is -9. And then on bottom I have -3 plus 5, which is 2. -9/2 is perfectly fine to leave that as, and so we will. Okay. Lots less work than creating tables, isn't it? Yeah, it is. So let's look at a few more theorems with some different features of limits that are super helpful for us. In particular, the first example we just did over here, the first one right there that was -x² plus 1, is what we call a polynomial. And the second one that we did, number 2, is actually called a rational function because of the ratio. So these 2 properties apply to the exact problems we just did. They say that if I have a polynomial, the limit of p of x is actually equal to plugging in the value into the polynomial, just like we just did on the first example. And we kind of justified it, right? We wrote out a little bit of why that was working with all of the limits that are working behind the scenes at our disposal. The second one says that if I have a rational function, I have the same ability. Again, as long as the denominator is not 0, then I can simply evaluate my rational function by plugging in the limit that x is approaching. As x is approaching c, I can use that c value and I can replace all my x's. So again, everything you want to be true is happening. Life doesn't usually work that way. So be happy right now that it is. It's good news. There's one more, but I think a few of you are still writing, so let me pause. Okay, I think we're good. The last one talks about what happens when we have radicals. Oh, there's 2 more. I'm sorry. Radicals and then composites. Radicals. So radicals have, again, the same kind of property that rationals and polynomials did. I can take the x approaches c, and I can use that value c, and I can evaluate it as long as the c value is positive when the index is even. Okay, so you'll remember as soon as I tell you why that's necessary, but when we're talking about the square root of negative numbers, what kinds of values come out of that? Imaginary. They're imaginary numbers. And there's nothing wrong with imaginary numbers. Let me just say that right quick. But we're working in the real number system for calculus. So we're not dealing with imaginary numbers at all this semester. So if you don't like them, you're in store for good things. No negative numbers underneath radicals. Now, if you have an odd radical, then it's perfectly fine to have a radical, or a radicand, the value underneath, to be negative. What is the cube root of -1? It's -1, yeah. So the thing about odds is that when I multiply something together an odd number of times, it can still be negative, right? -1 times -1 times -1 is still -1. That can't happen with even number or with even indices when we're working with radicals, okay? So that's the conditions here at the end. For all c when n is odd, for c is greater than 0 when n is even. We're just making sure we get real numbers out of our equations. Okay, is everybody good on that? Okay. And then the last one for the theorem that we're going to encounter right here is the composite function. So composite function is what happens when we have a function embedded inside of a function. I'll give you an example here on the slide here in just a second. But again, what you hope to be true is you still can simply evaluate x at the number c. So you just plug the c in for the x's. So what does a composite function look like? Again, I know you've seen these before, but we'll use some of the ones that I just did. If you had something like x plus 2, this is a composite function because there's a function x plus 2, inside of the function that's a square root. Okay, so a function inside of a function. Those are composite functions. And again, they work just like you would hope that they would. Okay, so we're going to do a few examples using these properties because they're so convenient to use. So let's take a look at number 3. What I was just told in all of the stuff before, in particular the one about rational numbers, is that I am allowed to simply plug the number 3, in this case, because it says x approaches 3, in for x. And can somebody tell me what happens? Yeah, and it isn't even just the problem with the 0 in the denominator. There happens to be a 0 in the numerator too, correct? Okay, so that doesn't have to happen. I mean, you could have a 0 in one place and not the other. If there was 0 on top, the answer would just be 0. The 0 on the bottom only, we'll encounter that in a little bit and I'll tell you what we do. But when we have a 0 in both of those locations, it's a very special fact. What it means is that I have the ability to go back to the function I started with and I have the ability to factor it and reduce it. Graphically, what this actually means is there's a hole in your graph. So anytime you get 0 over 0, this tells you two things. One, from a graphical perspective, there's a hole in your graph. And number 2, I'm going to be able to factor and reduce something. Now, I still may end up having a 0 somewhere. Like, that's a possibility. But when I factor and reduce, I should eliminate the fact that I've got a 0 on top and on bottom, okay? So this is where you need to be a little careful about your notation. So we are going to rewrite limit because we are not plugging in the number 3 yet. Until I actually plug the number 3 in, I need limit written at the beginning. It's kind of like when you're dealing with radicals. Until you actually take, for example, a square root, the square root notation stays on top of what you're working with, right? You don't just not write it down until you want to put it back in there. It doesn't work like that. So in a very real way, what we're trying to do is create a statement that's equal to the one before, and we're doing it by factoring. Now, the top does not need to be factored. It's just 3 minus x. How does the bottom factor?
3 minus x.
Close. Okay, x plus 3 and x minus 3. Okay. Is that good for the denominator? Now, there is not an absolute perfect match between top and bottom. Yes?
You could factor 3 minus x into the negative sign, then x minus 3.
Yes, that's our next step. You're right. So if at this point there's a perfect match from top to bottom, you cancel them out and you move on. Here, there's not a perfect match, but 3 minus x and x minus 3 are almost the same thing. In fact, they are the same thing except for the fact that one of them is the negation of the other. And so just like Jules said, if you take the top, and I'll go ahead and cut this and repaste it, and you were to take out a negative, you would actually end up with negative 3 and plus x, which is the same as x minus 3. And now it actually does match what's on bottom. Right? I know the order is different, but you can switch order. That's a commutative property of addition. So what I'm left with is, again, limit, because I haven't done it yet, of a negative 1 on top and an x plus 3 on bottom, and my x is approaching 3. So this is where WebAssign is not your best friend. WebAssign is probably not going to force the kind of structure that I'm going to expect when you get to your test or on a quiz. When you do a quiz on this, and it's like, I think it's going to be next Friday, actually, the quiz on this. When you get to the quiz on this, I expect to see limit at every single point along the way because it's not equal to the previous step without it, actually. It's different. It's like writing a whole bunch of things and saying, oh, I've got the square root of 48, and then rewriting and saying, okay, well, 48 is 2 times 24 is, and you keep going. If it doesn't have a radical over the 2 times 24, it's not equal to the square root of 48, right? You've left off part of the things that make it equal. The same thing's true about a limit. So at the point when you actually plug the number 3 or substitute the number 3 in for x, that's when you can stop writing limit. So I have -1 on top, I have 3 plus 3 on bottom, and this time it eliminated both zeros when I did that factoring and reducing. So I have an answer of -1, 6. All right? Algebra. So one of the types of factoring you did along the way, and in particular on this one, was difference of squares, right? So I'm not talking at length about a ton of factoring, and we're not going to be doing a ton of factoring in this class. But from time to time, it's going to crop up, and you're going to need to be able to do it, all right? Here's another one that does need some factoring. Oops, I skipped one. Oh, it's on the same slide. I missed it. Number 4 is another one that needs some factoring, but it's not difference of squares factoring, right? They're trinomials on top and bottom. So let me make one comment before we just start, like plowing into let's just factor everything. Sometimes you don't need to factor. So the only time you need to factor is when you plug the number in, you get 0 over 0. So don't factor if you don't have to, okay? It's not like somebody's trying to trip you up necessarily, but sometimes you're dealing with a rational function and you just simply don't have to factor it, right? I mean, it doesn't end up being necessary. Maybe it does factor, but it doesn't matter if it factors. You don't need to do it. So we want to make sure every time that we actually need to factor before we try to do so. So this time my limit is x approaching 4. So I've got 4 squared. Where's my stuff? Minus 5 times 4 plus 4 over 4 squared minus 2 times 4 minus 8. So you need to know, what do I get on top, what do I get on bottom? Yep. So it does need factoring, but it does not just because I saw a polynomial on top and a polynomial on bottom. It needs factoring because I got 0 over 0 when I tried to simply plug the numbers in. Okay? So now we're going to factor. So let's see how much we remember about factoring. That might be a scary question. I hope not. So we've got the top. We've got the bottom. How will x squared minus 5x plus 4 factor? Joel?
X minus 1. Or no, x minus 1, x minus 4.
Yep, you're right. X minus 1 and x minus 4. Okay, so if it's been a hot minute since you've done any kind of factoring, let's actually talk about how you can think about it again, and I'll do the denominator where we think it through. So the best case scenario when you're working with something you need to factor is that you have x squared at the beginning and not like 3x squared. Because if it's x squared, then it's always an x and an x. That's friendly. The next thing you do is you look at the sign at the end. The sign at the end of this one's negative. When it's a negative, it means there's one negative and there's one positive. The one that Jewel did for us had a positive at the end. The positive at the end means that the signs have to match, because a positive times a positive is a positive, or a negative times a negative is a positive. And they have to match and be negative because the sign in the middle is a negative. And that's why these ended up being both negatives on the top. Then I need two numbers, in the case of the denominator, that multiply to 8, and their difference is 2. 4 and 2. So I have kind of options, right? There's a 4 and a 2 here, or I can do a 2 and a 4 like that. And I need to make sure that whatever I pick will yield a negative 2. So which one of my values needs to be negative, the 4 or the 2? Yes, the 4. So this is a 4 and this is a 2. Now, let me just tell you, that's all true about factoring in general. I've got a college algebra class right now where we just talked about factoring, okay? And everything that I just did for you is what we talked about the other day, but like in slow motion, right? Because they're learning it from a different point of view at the moment. You actually should know that one of your factors has to be x minus 4 on top and on bottom. Guaranteed without a doubt. Why? Because the limit is approaching 4, and that's what causes it to be 0 over 0. So in some fashion, as you're deciding to factor this, you can almost kind of reason it out from what has to happen. What has to be true in the end? Well, I have to have x minus 4 on top, and an x minus 4 on bottom, and I can build whatever the other factor is around that even faster if I think through it from that perspective. So sure enough, these x minus 4s will cancel. I'm still not going to plug the number in. I'm going to write one more step. If you don't want to write one more step and you want to plug it in there, I'm not going to scream and holler and take points off. But I do still have an x minus 1 on top and an x plus 2 on bottom. And I am going to put the number in as, well, actually, I'll just write it over here to the side. 4 minus 1 over 4 plus 2. So 4 minus 1 is 3, 4 plus 2 is 6. And I'll reduce whenever I have the ability to do so. So I have 1/2. I prefer fractions. If you turn it into a decimal, it's okay, as long as it's not don't tell me 0.3 repeating. We're not going to do repeating bars. That's not going to work for us. It's not preferable math notation. So fractions are generally used more, but if you wrote this as 0.5, it would be totally fine. Okay? Any questions on this one? Because the last one is by far the most interesting. Okay. So this one's got radicals. And you might be thinking, okay, well, I didn't do a whole lot of factoring of the radicals back in the day. You probably didn't. Neither did I, for that matter. So this one we deal with in a little bit different way. But before we get too far in, again, we want to make sure that it's necessary to do anything at all. Right? Maybe I can just plug the number in and it's good to go. We'll find out very quickly that it's not. So what happens if I plug the number 0 in on top and on bottom? Because it's x approaches 0. Yeah. 0 over 0. Now, it's still true that it's going to be able to reduce. It's just not doing it from the polynomial style factoring that you're accustomed to. Okay? You ready to see how it works? Okay. So I'm going to shift this over. It is wise for you to make mention somewhere along the way that you've sort of mentally checked that at least before you get going. But I just don't want to rewrite right now. So what we're going to do, and what the sort of the key here is that we're going to rationalize the numerator. I'm going to call it numerator and just abbreviate. So I talked to my algebra students just the other day too and told them I'm not a big fan of rationalizing because there's not a whole lot of applications of why it's super necessary. This is one of the places where it is necessary. If you don't know how to rationalize when you get to this point in a calculus class, you're stuck and there isn't anything else you can do, all right? So rationalizing has to do with trying to get rid of those radicals on top. And that might not seem like it's all that, helpful to do, but it is. So what we need to do to get rid of the radicals on top and turn them into rational numbers is you multiply by what's called the conjugate. So a conjugate of a plus b is a minus b. That's just a general statement, okay? So we happen to have radicals here. So the conjugate of the square root of 2 plus x minus the square root of 2 is actually the square root of 2 plus x, just like that, and then plus the square root of 2. Okay? It's the exact same expression that's on top, just the sign between the radicals is different. But anytime, of course, that you're dealing with fractions and you multiply the numerator by a quantity, you have to do the same to the denominator. So we're going to multiply the top and the bottom by the same quantity. So why are conjugates so helpful? Well, I'd like to take a step aside. You've already done one today, but you didn't probably think about it from this perspective, where you had two conjugates and you broke them apart. You did it over, there. Nope, it wasn't there. It was there, problem 3. On problem 3, you had x squared minus 9, and they broke apart into conjugates, x plus 3 and x minus 3, right? And that happens, and it creates a difference of squares formula that you memorized somewhere along the way, undoubtedly. Well, that always happens when we're multiplying, oops, too far again. When we're multiplying conjugates together, we end up always getting the first value squared, a subtraction sign, and the last value squared. In particular, what really happens is the inner and the outer terms, if you're thinking from the perspective of like the acronym FOIL, this inner and this outer terms, they cancel. They're the exact same thing with opposite signs. So check it out over here. If I try this, if I were to multiply these two together, and I were to multiply these two together, they're exactly the same thing, but one of them's positive and one of them's negative, right? Yeah, it's like poof, they're gone. And the cool thing is because it's radicals that are involved, that when we square them, it cancels out the radical, right? So when I take the 2 plus the square root of 2 plus x and I square it, which I'll do it in a minute, but what's going to happen? I just get 2 plus x, right? And the same thing on the next term. So again, I have to do the subtraction sign, and then I've got the square root of 2, and I'll square it. Now, the denominator doesn't do anything beautiful. It just ends up being multiplied by itself. So don't go getting fancy and even distributing on the denominator. It won't be necessary. Just rewrite it as it is. Just like that, okay? Now, if I continue on, I've forgotten something. What have I forgotten? The limit. Yes, indeed. So I still need to note that I'm taking the limit as x approaches 0. Now, do you have to show this step where I've got the quantity squared? You don't have to. If you jumped from here to the next step, which was 2 plus x and then minus x for me, that would be totally reasonable. I just want to make sure everybody is seeing what is happening by showing that step, at least this time. Oops, sorry. Thank you. This is what happens when I zoom in and out too much, is that I lose things. Okay, is everybody good? Okay, so part of that numerator simplifies. What simplifies? The 2's simplify. That's great. But there's actually one other thing that simplifies. The x's. So right here, this x and this x simplify. And do you know what? That's good news. Because those x's being in there is what's causing that 0 over 0 that we got at the very beginning. Right? If I cancel that x out of the numerator, what does my numerator now become? 1. It'll be a 1. And if there's a 1 in the numerator, I don't have a 0 in the numerator anymore. And that was actually my goal all the way along. So I actually now have the limit as x approaches 0. I'm sorry, guys, of 1 over the square root of 2 plus x plus the square root of 2. I can plug in the number 0. So I have square root of 2 plus square root of 2 on bottom, which is 1 over 2 square root of 2. We would rationalize that by multiplying by the square root of 2 to give me square root of 2 over 4. And that would be the solution for my problem. Sorry, didn't mean to run that through so fast at the end, but yeah. Okay? That's actually exactly where I wanted us to end, so that's good news. We will pause there for today. We will pick up with Theorem 1.6 on Monday. Have a wonderful weekend.